Consider the system of linear equations given by Ax equal to b, where A is the matrix here, X is the tuple x1, x2, x3, x4, and x5, and B is a tuple 2, 4, 6. Do you see a solution to this system right away? Maybe not that quick. So let's write out the system in full and see what it is like. So the first equation will be minus 4x4 plus x5 equals 2. The second equation will be given by x1 minus x4 equals 4. And the third equation is given by x2 plus x3 plus 3x4 equals 6. Now, I'm going to rewrite this system as follows. If I add 4x4 to both sides of the first equation, I get x5 equals 2 plus 4x4. And if I add x4 to both sides of the second equation, I get x1 equals 4 plus x4. And finally, adding minus x2 minus 3x4 to both sides of the third equation, I get x3 equals 6 minus x2 minus 3x4. Now, this system is equivalent to the original system. And what's more, the variables x2 and x4 appear only on the right-hand side. Once we have fixed a value for x2 and x4, we can solve for the remaining variables. And in particular, if I set x2 and x4 to 0, we get that x5 has to be 2, x1 has to be 4, and x3 has to be 6. But these are precisely the right-hand side values. Is there a coincidence here? Well, the answer is this system is very special. If you look at each equation, you can find a variable that appears in that equation and no other equation. For example, in the first equation, x5 is such a variable. It doesn't appear anywhere else. And in the second equation, x1 is such a variable. In the third equation, both x2 and x3 appear nowhere except in the third equation. And if those variables have coefficient 1, then you can easily get a solution by setting all the other variables to 0 and setting these variables to the right-hand side values. This is really nice, but can we always transform a system of linear equations into an equivalent system that looks like this? Before we can address this question completely, let us rewrite this system a bit. By reordering things, I can write the system as the following. So I bring the third equation into the first equation. And in the second equation, I'm going to put the third equation of the system. And the third equation will be the first equation of the system, but I'm going to write x5 first. Now, the coefficient matrix of this system is given by this. This matrix satisfies a number of properties. First, the leftmost non-zero entry in each row is 1. Such a 1 is called a leading 1. Second, all the entries above and below these leading ones are all 0. So these are my leading ones. And also, the leading one in a particular row is to the right of any leading one above it. This matrix is said to be in reduced row echelon form. And the definition of reduced echelon form is as follows. So the first two properties are what we have already mentioned. But there's a third property that is satisfied vacuously by this matrix, is that any row containing only zeros is at the bottom. And here's an example of a matrix in reduced row echelon form that has a row of zeros. The reason why we're interested in matrices in reduced row echelon form is because if the system A is equal to B is such that A is in reduced row echelon form, then we can easily tell if this system has a solution and give one if it does. Suppose that A has a row of zeros in row I, and Bi is not 0. This means that in the system, we have an equation that says 0 equals to Bi. But if Bi is non-zero, this is not possible. So Ax equal to B has no solution in this case. For example, if A is 1, 2, 0, 0, and B is 3, 4, and X is X1, X2, then the system Ax equal to B has no solution, because if you write the system out in full, this is what it is. No matter what you choose for x1, x2, the second equation will never be satisfied. But if this doesn't happen, then there's always a solution, and we can set all the variables that correspond to the leading ones to the right-hand side values, and setting all the remaining variables to 0. That will give us one solution. However, doing that does not necessarily give us all the solutions, and that's something that we'll address in a later video.